So every time you click a link or, log into a mobile app or launch a streaming video, there is this frantic, incredibly dense conversation happening right under your fingertips.
Yeah, and you don't hear it at all.
Right, you certainly don't see it on your screen.
Yeah.
But right now, your phone or your computer is exchanging millions of invisible numeric messages with servers scattered all over the globe.
It is a completely silent, continuous negotiation. I mean, we take the reliability of the modern web for granted every single day, right? You open dozens of tabs and just expect instant results.
Oh, absolutely.
But beneath the polished user interfaces, the internet is essentially this massive, chaotic, distributed system. And to prevent that system from collapsing into total chaos, it relies on a perfectly synchronized, universal global language to mediate, well, every single interaction.
And today, our mission is to uncover that language. We're doing a deep dive into the architecture of HTTP status codes using this incredible document we have called statuscodesoverview.md.
It's a great source.
Yeah, it really is. We were going to decode these hidden messages so you understand the underlying mechanics of what your devices are constantly whispering to the data centers that hold your work, your entertainment, and your personal information.
Which is a lot of data.
Exactly. But to really appreciate the elegance of these numbers, we have to look back at the architectural landscape before they existed, back when computer networking was essentially the Wild West.
Oh, the landscape before the early 1990s was heavily fragmented. I mean,
Right.
you had various systems on early networks communicating through entirely custom protocols.
It was just a mess.
Total mess. If a developer built a server, they basically had to invent their own way of telling a client application whether a request was successful or not. There was absolutely no standardization.
So if I'm a developer trying to build a client that talks to, say, 5 different databases across the country, I might ask the first server for a file, and it returns a string saying success.
Right.
And the second server returns the turning. Okay? The third server maybe just drops the connection entirely, and the fourth one returns done.
Yeah, which is incredibly brittle. Building scalable interoperability was just a nightmare.
I can imagine.
So when Tim Berners-Lee and the early architects of the World Wide Web were drafting the first HTTP requests for comments, the RFCs, that govern internet standards, they recognized that relying on arbitrary text strings to convey system state was completely unsustainable.
Because humans can read that, but computers can't.
Exactly. If an application has to load up a text parser, read human language, and guess the intent just to know if a file was downloaded successfully, the latency and error rates would be astronomical.
It's like trying to order a highly specific, complex meal in a million different restaurants where every menu is written in a language you don't speak.
That's a great way to put it.
But then, suddenly the global restaurant industry agrees to use this universal system where everyone just points at numbered index cards, 1 through 5.
Yeah, and that shift was monumental. By mandating a standardized numeric index, HTTP shifted the internet's communication layer from subjective text parsing to objective data evaluation.
Right, because numbers don't change based on the language you speak.
Precisely. A numeric code like 200 or 404 can be instantly evaluated at the machine level. So a browser written in C++s, or a mobile app built in Kotlin, or a massive back-end microservice running on Go can all read a 3-digit integer and immediately execute their next logic branch.
It creates this foundational consistency. Whether you are hitting a massive endpoint at Google or Amazon, or just querying a tiny personal blog hosted on a Raspberry Pi in someone's basement, the communication rules are identical.
And that consistency is the bedrock that allowed the API economy to flourish. I mean, without a shared numerical language, the concept of modern microservices, where dozens of different applications seamlessly pass data back and forth to render a single web page, it would simply be impossible to orchestrate.
Which brings us to the structure of the language itself, because the architects didn't just throw a random list of numbers at developers.
No, they didn't.
They built a highly organized taxonomy. It's grouped into 5 distinct categories, indicated by the very first digit of the code. And the best way I like to visualize these categories is by thinking of them as traffic signals for internet routing.
The traffic light analogy maps perfectly to how requests travel. So the 200 level codes, the 2XX group, serve as the green light.
The request was received, understood, and successfully processed.
Exactly. Then the 3XX codes represent a yellow light, or a detour. It means the client needs to take one additional routing action to reach its destination.
Okay, making sense so far.
Then we hit the red lights, the 4xx client errors, which indicate a problem with the request you sent, and the 5xx server errors, which are basically the emergency signals indicating the server itself is failing.
Okay, wait. I want to pause on that traffic light analogy and push back a little on how we define those red lights.
Yeah.
Because from a user's perspective, both a 400-level error and a 500-level error result in a broken web page or failed app load. They both look like a red light to me. So if we stick with the driving metaphor, a 400-level error means I drove my car into a wall, but a 500-level error means the road itself collapsed underneath me.
That is spot on. And that distinction is the single most critical piece of telemetry a developer relies on.
Really? Just that first digit.
Yeah, because a 4xx error means the fault lies entirely with the driver, the client application. You requested a URL that doesn't exist, or you forgot to include your authentication token, or maybe you submitted an invalid form, you drove the car into the wall.
Right, fault.
But a 5xx error means the server infrastructure failed. The database went down in the middle of a query, the application code threw an unhandled exception, or the data center lost power. The road collapsed.
And that immediately dictates the engineering response, right? It isolates the blast radius of the problem.
Yep. Exactly. When an on-call software engineer gets paged at 3:00 a.m., the very first metric they look at on their monitoring dashboard is the ratio of 4xx to 5x codes.
Oh, wow. First thing they check.
Always. A sudden massive spike in 400s usually means a third-party bot is scraping their site incorrectly, or maybe a user is hammering a broken link. They probably don't need to wake up the whole team for that. But a spike in 500s, that means their infrastructure is actively burning down.
Okay, let's dive into the actual daily commute, the specific numeric codes we are generating every time we open a browser. And the absolute workhorse of the internet is the 200 OK.
Right, absolutely.
Every time you successfully load a page or fetch a product catalog or read an article, you are generating 200s. But it's far from the only green light.
Yeah, when you interact with a modern RESTful API, you see a much wider vocabulary of success. Take 201 created. You see this when your request successfully generates a brand new row in a database.
So like making a new account.
Exactly. When you hit submit on a registration form and create a new user profile, the server doesn't just say 200 OK. It replies with 201 created, and crucially, it often includes a location header in the response, giving the client the exact URL of that newly minted profile.
Oh, that's clever.
Yeah.
Then there is 204 no content, which feels almost paradoxical to me. It's a success code, but it actively tells the browser not to expect any data back.
It sounds weird, but 204 is an incredibly efficient optimization tool. The most common use case is deleting a resource.
Okay.
If your email app sends a delete request to remove a spam message, the server wipes the record and replies with a 204. It's essentially the server saying, I executed your command perfectly, the email is gone, and because it's gone, I have 0 bytes of data to send you in return.
That makes total sense. Okay, let's look at the red lights where things start to break down.
Right.
We all know the 404 not found. I mean, it's culturally ubiquitous at this
You
point.
can see it on t-shirts.
Right. You ask for a specific URL, and the server checks its routing table and says, I have no idea what you're looking for. Oh, and 409 conflict, like when you try to register an email address that already exists. But the 400-level errors get incredibly granular. Take 400 bad request versus 422 unprocessable entity. At first glance, they sound like the exact same thing.
They do, but the difference lies in where the parsing engine chokes. A 400 bad request is usually a structural syntax error.
Like a typo in the code.
Kind of. Imagine your app tries to send a JSON payload to a server, but it's missing a closing bracket. The server's parsing engine literally cannot read the file. It throws its hands up and issues a 400.
But with a 422.
With a 422 unprocessable entity, the syntax is flawless. The JSON is perfectly formatted. The server successfully parses the payload, but the data inside violates a strict business rule.
Give me an example.
Sure. Say the payload contains an email address and a password, but the password is only 3 characters long and the database schema requires 8. The entity is technically sound, but practically unprocessable. And then you also have things like 429 too many requests, which is all about API rate limits.
Right, like if a spam bot is hitting the server too fast, the server throws a 429 to protect itself.
Exactly.
I want to shift gears to what I think is the most fascinating psychological distinction in these codes. The web's identity crisis. I'm talking about the mechanics of 401 unauthorized versus 403 forbidden, because these dictate completely different user experiences. I always think of it like dealing with a bouncer at an exclusive club.
That is the perfect analogy. A 401 unauthorized happens at the very first layer of security authentication. The server inspects the incoming HTTP request and looks for an authorization header, like a session cookie or a JSON web token.
And if it's not there?
If that header is missing or if the token has expired, the server throws a 401. It is the banser saying, "You don't have a wristband. I have absolutely no idea who you are."
But a 403 forbidden is a much deeper rejection.
Very much so. A 403 means the authentication was successful, but the authorization failed. The server read your token, it successfully decrypted it, it knows exactly who you are, say, user ID 8675.
Okay.
But when it checked the database, it saw that user 8675 only has a guest role, and the endpoint you are trying to reach requires an admin role.
Ah.
It is the bouncer looking at your verified driver's license, pulling up the clipboard and saying, "I know exactly who you are, but you are not on the VIP list to enter this room."
And the brilliance of this distinction is how the client application reacts autonomously. Because it's an objective numeric code, the application doesn't have to guess what went wrong.
Right. It just knows.
Yeah, if the app receives a 401, it automatically triggers a redirect to the login screen. It knows it needs to establish identity. But if it receives a 403, it knows you're already logged in, so presenting a login screen would be an endless, frustrating loop.
Which is terrible user experience.
Exactly. So instead, it surfaces a permission error or maybe prompts you to upgrade your subscription tier.
It governs the entire flow of application state without any human intervention.
So we've covered the daily commute,
Yep.
basic data fetching, form submissions, logging in, but the modern internet handles massive asymmetrical workloads. We are dealing with multi-gigabyte file uploads, real-time bidirectional streaming, massive background processing. How does the architecture stretch to handle these really heavy operations?
Well, the architecture uses specific ranges, particularly the 100s and specialized 200s, to manage TCP connections and bandwidth efficiency. Let's examine a scenario where you're trying to upload a massive, uncompressed 10 gigabyte 4K video file to a cloud storage provider.
Oh man, if the client just started indiscriminately shoving 10 gigabytes of data through the network pipeline, and the server wasn't authorized or didn't have the disk space to accept it, the wasted bandwidth and time would be catastrophic.
To prevent that, the client sends a preliminary, lightweight request containing just the HTTP headers, including a specific header called expect 100 continue. It's essentially asking permission to consume bandwidth. The server evaluates those headers, checks its storage capacity, validates your token, and if everything looks good, it returns a 100 continue status code.
And only then does the client actually open the floodgates and transmit the heavy payload.
Right.
It's a brilliant handshake. Then we have 101 switching protocols. Standard HTTP is, by design, a stateless request-response protocol. I ask, you answer, and then we hang up the phone.
That's how it normally works.
But if I'm looking at a livestock ticker or playing a multiplayer game, I need a connection that stays permanently open.
Right, and in those scenarios, the client sends an HTTP request asking to upgrade the connection to something like WebSockets. The server evaluates the request, agrees, and returns a 101 switching protocols.
And what happens then?
At that exact millisecond, the connection drops the standard HTTP rules and transforms into a persistent two-way TCP stream where data can flow continuously in both directions without needing new requests.
That is so cool. Let's talk about asynchronous operations, the 202 accepted code. I see this a lot in modern systems, where a user asks an application to perform a tremendously heavy task. Like, say you click a button to generate an annual financial report spanning millions of database rows, or you ask a server to process a complex machine learning model. Server obviously cannot do that instantly.
No, and if the server tried to hold the HTTP connection open while it generated that massive report, the connection would eventually time out and your browser window would just freeze indefinitely.
Which we've all experienced on poorly built sites.
Exactly. So instead, the server receives the request, validates that it has the parameters it needs, places the job into a background message queue like RabbitMQ or Kafka, and immediately fires back a 202 accepted.
So it's like a restaurant. You placed your order with the waiter, they accepted it immediately, but your food is still cooking in the kitchen.
Yes.
It frees up my browser to go do other things while the server churns away in the background.
It neatly decouples the client's interface from the server's compute time.
Now we need to discuss the yellow lights, the detours. Specifically, the architectural difference between a 301 moved permanently and a 302 found.
This is a distinction that has massive implications for search engine optimization and network caching. A 301 moved permanently is a hard directive.
Like, do not ever come back here.
Right. When Google's web crawler hits a URL and receives a 301, the server is stating that the old URL is dead and the resource has a new permanent home. Google will actually update its search index, transferring all the ranking authority from the old link to the new one.
Oh, wow.
Furthermore, your browser will permanently cache that redirect. So the next time you type in the old URL, the browser doesn't even bother asking the server. It just routes you straight to the new destination.
Whereas the 302 found is essentially just a temporary detour.
Yeah, with the 302, the server is saying, the resource you want is temporarily located over here, but keep using the original URL for future requests. You encounter 302s constantly in authentication flows.
Like when you try to access a protected dashboard.
Exactly. The server throws a 302 to bounce you to an authentication provider, and once you log in, it bounces you back.
But out of all the 300-level codes, the absolute marvel of internet engineering, the one that keeps global bandwidth costs from bankrupting the telecom industry, is 304. Not modified. If 304 didn't exist, the modern web would slow to an absolute crawl.
It really would, because a modern web page is an incredibly heavy payload of high-resolution images, massive JavaScript bundles, intricate CSS style sheets. If your browser had to download every single one of those assets from scratch, every single time you clicked a new link on a website, the latency would be unbearable.
So how does the server prevent that without serving stale, outdated content? If 304 means the browser just uses its local cached copy, how does the server confidently know what the browser has stored on its hard drive?
It relies on a brilliant system of cryptographic hashing and timestamping. When you download an image for the first time, the server includes an HTTP header called an E tag.
An E tag?
Yeah, which is essentially a unique alphanumeric fingerprint of that specific version of the image. And the server also includes a LAFT modified timestamp. Your browser stores the image, the E tag, and the timestamp in its local cache.
Okay, so then a week later, I navigate back to that same web page. What happens?
Your browser looks at its cache and says, I already have this image, but I don't know if it's outdated. So it sends a tiny microscopic request to the server with a header called if none match, and it includes that E tag fingerprint.
It's asking the server, does the current version of your image still match this fingerprint?
Exactly. The server quickly hashes its own file, compares the two fingerprints, and if they match perfectly, it doesn't send the heavy image data back. It simply returns a 304, not modified.
And the browser immediately loads the image from the local hard drive. It saves megabytes of bandwidth by transmitting only a few bytes of headers. That mechanism is operating thousands of times a second on your machine right now.
It is an incredibly elegant solution to the fundamental problem of caching in distributed systems.
Okay, so we've explored how the architecture handles massive files and caching efficiency. Now I want to look at how the web handles highly specific, nuanced failures. Because servers aren't just the black box that spits out generic errors.
No, they're very communicative.
Right. The routing infrastructure acts like a multi-layered defense system, knocking out bad requests at different tiers using advanced 4XX codes. Let's imagine a scenario where a developer is building an automated script to push data into a cloud API.
That's a great way to map these advanced codes because they cascade down the architectural layers. Let's say the developer script fires its first request and the server returns a 410 gone.
Now, how is that different from our standard 404 not found?
Well, a 404 is ambiguous. The server simply cannot find a match in its routing table. But a 410 gone is an explicit, definitive tombstone.
The tombstone.
Yeah, it means this API endpoint absolutely used to exist, but we have permanently deprecated it and it is never coming back. It is a loud signal to developers to stop requesting the resource and update their client code.
Okay, so the developer reads the API documentation, updates their script to point to the correct new URL. They fire the request again. This time, they hit a 405 method, not allowed.
Now, the URL is perfectly correct, but the HTTP verb they used is wrong. The developer script is trying to send a PST request, an action designed to create or modify data, but they accidentally pointed it at a read-only endpoint that only accepts GET requests.
And the server just blocks
The
it.
server immediately rejects it. The door exists, but you are trying to push when you should pull.
Right, okay. So the developer catches the mistake, changes the script to a POST request targeting the correct right endpoint. They fire it again.
Yeah.
Boom, 415 unsupported media type.
This happens before the application code even tries to read the payload. The server inspects the content type header of the incoming request. Let's say the server is strictly configured to only accept JSON payloads. The developer forgot to set their headers correctly, and the script defaults to sending an XML document. The server sees the XML designation and immediately halts the transaction. It refuses to process a format it isn't designed to understand.
So they fix the content type header to JSON, fire it again, and they get hit with a 406 not acceptable.
This is the exact inverse of the 415. The 415 was about what the client sent. The 406 is about what the client demands in return.
What do you mean?
The developer script included an accept header, insisting that the server's response must be delivered in a legacy format, like a CSV file. But the modern API only speaks JSON. The server evaluates the demand, realizes it cannot fulfill the requested format, and returns a 406. It's a failure in content negotiation.
Wow. Okay, finally, the developer fixes all the headers. They have the right URL, the right method, the right payload format, and the right acceptance criteria. They hit execute, the script tries to push the data, and they receive a 413 payload too large.
And this is a perfect example of how these codes operate at different layers of the server stack. This rejection likely didn't even reach the application code.
Wait, really? Where did it get blocked?
It was probably intercepted by a reverse proxy or a load balancer sitting in front of the application, like Nginx. Nginx has a strict configuration capping incoming request bodies at, say, 50 megabytes to prevent memory exhaustion attacks. The developer's script tried to upload a 500 megabyte JSON file. The reverse proxy terminates the connection instantly with a 413 to protect the underlying servers from being overwhelmed.
When you lay it out like that, it proves that the internet isn't just stubbornly ignoring bad requests. It is a highly robust diagnostic framework.
Very much so.
The routing infrastructure is actively evaluating the method, the headers, the format, and the size of the payload sequentially, diagnosing the exact point of failure so the client can correct its behavior.
And enterprise architecture relies entirely on this precision. When a company is processing tens of thousands of transactions a second, they cannot rely on humans to parse log files to figure out why a data pipeline failed.
Right, there's just no time.
Exactly. They rely on the objective telemetry of HTTP status codes to trigger automated retries, alert infrastructure teams, or gracefully degrade the user experience.
It truly is a marvel of distributed engineering. So, the next time you see a 404 not found on your screen or an application throws a 500 internal server error, you aren't just experiencing a minor frustration. You are witnessing a critical piece of a 30-year-old communication architecture.
That's exactly right.
It is the invisible connective tissue that keeps billions of disparate devices, from smart refrigerators to massive server farms, speaking the exact same language. You don't need to memorize every single integer, but understanding the taxonomy, the green lights, the detours, the client failures, and the server emergencies, it really demystifies the mechanics of the web.
And, as we look toward the future, it's fascinating to consider how this numerical shorthand will have to evolve. HTTP was originally designed to facilitate communication initiated by humans using browsers, but we are rapidly entering an era dominated by autonomous AI agents.
That's a great point.
These systems will increasingly browse the web, scrape complex data sets, and negotiate directly with backend servers at blinding speeds without any human oversight. Will the current 5 categories be expressive enough? Or will the architecture eventually require an entirely new protocol extension, perhaps a 6xx or 7xx block of status codes designed exclusively for AI to AI resource bidding, autonomous rate limit negotiation, and machine consensus?
That is wild to think about. A completely new layer of the internet, invisible not just in its operation, but in its very design, built strictly for machines, talking to machines. The language of the web is far from finalized. It's actively evolving. So the next time you click a link and trigger that invisible cascade of millions of numbers, take a second to appreciate the sheer mechanical orchestration required to deliver that web page to your screen. Thank you for joining us on this deep dive into the hidden language of the web. Keep exploring the architecture around you, and we will catch you next time.